Hello and welcome to this Python tutorial. So here we are at the final round of regression with our last nonlinear regression model, which is the random forest regression. In the previous section we saw the decision tree regression model, so if now the decision tree regression doesn't have any secret for you, then you will perfectly understand random forest regression. Because a random forest is just a team of decision trees, each one making some predictions of your dependent variable, and the ultimate prediction of the random forest itself is simply the average of the different predictions of all the different trees in the forest. And speaking of that, at the end of the last section about decision trees, I asked you an enigma. What do you think we'll get in terms of prediction and in terms of visualization? Do you think we'll get the shape of some stairs like we had for decision trees? And do you think we'll get a poor prediction like decision trees, or a much more accurate prediction that would hopefully be close to the 160K salary that this future employee was supposed to have in its previous company? So that's what we are about to find out in this tutorial. And to find out about that, let's build random forest regression. So let's go to our file explorer to set the right folder as working directory. So we go to machine learning AZ, part 2 regression. And here, as you can see, this is the final round. Well, this is actually the last regression model we were making, which is the random forest regression. So let's open this folder, and that's the right folder we want to set as working directory. Make sure that you have the position salary CSV file. And if that's the case, click on this little button here to set this folder as working directory. All right, and now let's build the model. So we'll go to our regression template. And this time we will not take everything up to here with the standard visualization of the regression results, but we'll take that instead, because I'm actually giving you a hint. Random forest might be a non-continuous regression model because simply it's a combination of some non-continuous regression models that are the decision trees themselves. So we don't want to take that. We will get the same problem as what we got in decision trees. So we will take this code section here to visualize the regression results. Okay, so I'm going to copy everything, copy, paste it here, and then I'm just going to remove this section because it is not appropriate for our model. So you already have a hint, and you might guess what we will obtain in terms of fitting curve and prediction. Okay, so now let's change the basics. Let's replace regression model here by random forest regression. And here as well. Right. And now let's do the important thing, the creation of our regressor. So, as usual, we are going to do it in 3 steps. First step is to import the right class for the job. Second step is to create an object of this class, which will be our random forest regressor itself. And then third step is to fit our random forest regressor to our dataset using the fit method. So let's do it. The class that we're going to import is the random forest regressor class, another very intuitive name. And we are going to import it from the sklearn.ensemble, here it is, library. So from a scalar.ensemble library, we import the random forest regressor class. So that's the class with capital R, capital F, and capital R again. And now, second step, we create an object of this class, which is the random forest regressor itself. So we're going to call it regressor as usual. Here it is. Now we call the class random forest regressor, so I'm going to copy this. All right, copy, paste it here, and then now we input the arguments. Great. So let's inspect this class to see what arguments we need to input. So Command I, and here we go. These are the parameters. So the first parameter is n estimators. Can you guess what it is? Well, it's actually written here. It's the number of trees you want to have in your forest. So that's a very important parameter. The default value for this parameter is 10 trees, like we're building a random forest of 10 trees, but don't worry, we will try with a lot more than 10 trees. We will try with 100 trees, and let's go up to 300 trees. So let's input this argument, and estimators equals, and let's start with 10. Okay, so we'll start with 10 and then we'll try 300. Okay, so that's the first parameter, 10 trees in the forest. Great. Then the second parameter is criterion. And remember, this is a parameter that we had in the decision tree class that we used to build our decision tree regression model. So, it's the mean squared error that's taking the sum of the square differences between the prediction and the real result. So that's the default criterion, and we're not going to input it because that's the most common criterion, and this will work perfectly with our model and problem here. So great. Then as for decision trees, you have some optional parameters like max features. The default value for that is auto, so that's fine because then you see a lot of maximum parameters and minimum parameters. So that's some parameters you can use to improve your model. But let's focus on the essence of the random forest regression model. And so we'll just add this parameter random state as we did for decision tree regression. So we will just input here random state equals 0. Right. So basically what we're only interested in is the number of estimators, that is the number of trees in our forest. So we'll start with 10 and we'll try other values. Okay, so that's the second step, and now the last step, of course, is to fit our regressor to our data set. And to do this, we're using the fit method that we have to separate from our regressor object by a dot. And here we use the fit method as usual to fit our regressor object to our data set that is composed of x, the matrix of features, and y, the dependent variable vector. And now we're ready. The random forest regression model is ready to be built. So let's do this without waiting. And what does that mean for the whole code? That means it's ready to be executed. So right now we don't have anything to do. The only thing that we can do as an option is to play around with the number of trees and, choose the best team of trees to build a random forest regression model. So we'll just play around with this parameter and add some more trees and visualize the results and getting the prediction until we get something coherent. So let's do this. Let's execute the sections one by one. So first, let's import the libraries. Here we go, libraries imported. And now let's import the dataset. Here we go, dataset imported. And now let's build the random forest regression model. So as you can see, we shouldn't have any problems. So first, we're building a random forest of 10 trees. Here we go. The random forest is created. So as you can see, all the default parameters were selected automatically. And so now it's time to have fun. Would you like to start by predicting the result or visualizing the regression result? So let's perhaps do this step first, to try some different approaches of our model and then testing the different predictions. But first, before I execute this section, can you guess what is going to happen? With one tree we obtained the shape of some stairs, and it was a non-continuous model, and our previous decision tree algorithm was splitting the whole range of levels into separate intervals, and on each interval it considered the average value of the dependent variable salary. And actually, since we had only one value in the intervals, because we only had 10 levels, this average was only the salary of the level contained in the interval. So that was not interesting at all, and that's why we got a poor prediction. But here we have several trees, so we'll have several stairs. And therefore, how would you imagine a combination of stairs in one dimension? So try to pause on this video and try to predict what's going to happen. And now I'm going to select this section to see what we'll get. So what we'll get is the visualization of some random forest regression composed of 10 trees. And this is what we obtain. So we have the confirmation it's a non-continuous model, as expected, and therefore let's increase the resolution by reducing the step down to 0.01 to, get some more vertical lines that would represent better the non-continuity. So here we go again, let's take this and execute. Alright, that's better now. We visually see some vertical straight lines here that highlights better the non-continuity. So now let's enlarge this and let's interpret. Okay, so the answer to the enigma that I asked you in the previous section and that I was asking you again in this tutorial is that we simply get more steps in the stairs. By having several decision trees instead of one decision tree, we have a lot more steps in the stairs than what we had with one decision tree. And therefore we have a lot more splits of the whole range of levels, and therefore a lot more intervals of the different levels. So each straight horizontal line here, separated by these vertical lines, are one interval that is one split. And the fact that we get more steps in the stairs is actually quite intuitive, because, you know, if we get, for example, this prediction here for the 6.5 level, well, what happened for this prediction is that we had 10 trees voting on which step the salary of the 6.5 level position would be. And then the random forest took the average of all the different predictions of the salary of the 6.5 level made by all the different trees in the forest. And for example, if we take the 4th position level, 10 votes were made. Each of these 10 votes correspond to one prediction of the level 4 salary made by each one of those 10 trees. And then the random forest took the average of these 10 predictions, and this average is nothing else than the prediction of the level 4 salary made by the random forest itself. And so we get more steps because simply the whole range of levels is split into more intervals. And that is because the random forest is calculating many different averages of its decision trees predictions in each of these intervals. So that's what happened. It's quite intuitive. However, there is something important to point out here, is that if we add a lot more trees in our random forest, well, it doesn't mean we'll get a lot more steps in the stairs. Because the more you add some trees, the more the average of the different predictions made by the trees is converging to the same average. You know, this is based on the same technique, entropy and information gain. So the more you add trees, the more the average of these votes will converge to the same ultimate average. And therefore it will converge to some certain shape of stairs here. So that's important to visualize this as well. And now, since we have our intuition of the visualization of the random forest regression in 1D, let's see what happens with the prediction. So let's execute this, and can you predict what's going to happen? Remember, with our decision tree, we got a prediction of $150,000, but that was just the salary of level 6. So that was actually not very interesting. But here, as we just saw on the graph, there are a lot more steps in the stairs, so maybe we'll get a much more accurate prediction. Let's find out about that. Let's execute this, and here we go. We get a prediction of $167,000. So a little bit better than with one tree, but wait, we only have 10 trees in our random forest regression. We can build a lot more trees than 10 trees. We can build a random forest with 100 trees, and that's exactly what we're going to do right now to see if our prediction is getting better. So let's try with 100 trees. Here we go, 100 trees now. So let's rebuild the model, execute. Now the model is rebuilt. Let's have a look at it to see if we get more steps in the stairs. And that's what I was telling you. We multiplied the number of trees by 10, but the number of steps in the stairs doesn't seem to have been multiplied by 10. And that's for the same reason, an explanation of convergence that I was talking to you about. So actually this is the same idea. This is kind of the same stairs, but maybe that the steps were better chosen to make the ultimate prediction. So let's check that out. We're going to close this and see what happens in terms of prediction. So remember, with one tree we had a prediction of 150K. With 10 trees we had a prediction of 167K. And now let's see the prediction we get with 100 trees. So let's check it out. I'm going to execute this. The model is built. So here we go. And we get, wow, okay, really good. Now we get a prediction of 158K. So it's converging to the supposed previous salary of the employee. And you know, when we applied polynomial regression, the verdict was truth. This employee is not bluffing, and it's an employee that we're happy to hire because not only he's a good fit for the job, but also he's honest. And now it seems that with a random forest of 100 trees, the model is confirming that, because now we get a prediction of $158,000. But let's try if we can get closer to the supposed previous salary of 160K by, for example, increasing the number of trees to 300. Maybe we'll get an even closer prediction, because now the polynomial regression, I think, is still beating the random forest regression. I don't remember exactly the polynomial regression prediction, but I think it was actually even closer to 160K, or maybe nearly even. Well, let's see anyway if we can get a 160K prediction for our employees' previous salary. So let's check it out. We're going to try with 300 trees, and let's build this model. Here we go, new model created, new forest created with 300 trees. And now let's visualize these results, but we'll get the same things. We'll not get a number of steps multiplied by 30. We'll get the same shape as before. Here it is, as you can see, it's nearly the same. We get the same number of steps. It's just that the steps are actually better placed with respect to the salary axis for our specific problem. So now let's find out about the ultimate prediction, and I think we'll be able to conclude whether it's truth or bluff. So let's execute this line, and are you ready? Here we go, and we get, oh wow, we get now a predicted salary of 160K right in the spot. We hit the bullseye to predict our future employees' previous salary. And now the random forest regression is beating the polynomial regression model, because now we get a prediction that is almost the same as the real value. So right in the spot, congratulations, we actually made our final model. And now I just want to conclude this tutorial by making this transition to one of our future parts, which is actually part 10. In part 10, we will build some ensemble machine learning models. That is, some models that are a combination of several machine learning models. And you know, in machine learning, these are actually the best models. You know, when you have a team of several machine learning models, they can actually make an awesome prediction, because unless we have an Einstein machine learning model in our combination of machine learning models that is the only model to be right, well, you're more likely to get the correct prediction with 10 machine learning models predicting the same thing than with just one model. So that's actually what we did here. Well, we had a team of same machine learning models, which were decision tree regression models, but in the future we'll make a team of different machine learning models. So that's going to be very fun, that's going to be very powerful as well, and I look forward to getting there with you. So now I'm telling you congratulations for two things. First, for building this very powerful regression model, the random forest regression model, and second, for having built all our regression models. We built some linear regression models, some nonlinear regression models, some nonlinear non-continuous regression models, and some nonlinear non-continuous ensemble regression model. So congratulations, you're definitely on your way to becoming some experts in machine learning, but wait for what's coming next. So speaking of what's coming next, I look forward to seeing you in the next sections or next parts.